Section 4.3, Complex Roots of the Characteristic Equation. So last time we were looking at second-order linear homogeneous constant coefficient equations of the form ay double prime plus by prime plus cy equals 0, where a, b, and c are known constants and a is not 0. Let's call this equation star. Last time we looked for solutions of the form y equals e to the rt, and after some work, we got the characteristic equation ar squared plus br plus c equals 0. That's a standard quadratic equation. We used the quadratic formula, and we said in general you can find r as minus b plus or minus the square root of b squared minus 4ac all over 2a. So just to recap, we saw that in case 1, when the discriminant of the quadratic was positive, you got two distinct real roots. We'll call them r1 and r2. If we got two distinct real roots, then that means one solution will be, we'll call it y1. One solution is e to the r1t. A second solution, we'll call it y2, is e to the r2t. We also proved that not only are they both bona fide solutions, that they're in fact linearly independent because their Wronskian is non-zero. And then our theory said that therefore the general solution to the second order equation star, when you're in case 1, is c1 e to the r1t plus c2 e to the r2t. This is a two-parameter family of solutions, and it's in terms of the two roots r1 and r2. All right? And then we looked at case 2, what happens if the discriminant of our characteristic equation is 0. So that meant that we got one repeated real root, we'll call it r. So then one solution is e to the rt. Remember last time we said that we can't use e to the rt as the second solution in order to build our general solution because our second solution has to be linearly independent from the first solution. But what we found is we just declared that the way you get the second linearly independent solution is to take your first solution and multiply it by your independent variable, multiply it by t. So we got e to the rt is one solution, and t e to the rt is a second solution. And they're linearly independent. We proved this because the Wronskian of those two was non-zero. Once we have two linearly independent solutions, our theory said we can build the general solution. And remember what general solution means. When we write this as a general solution, it means every possible solution to that differential equation in the universe is covered by this. We haven't missed any. We have found them all. We said the general solution would be c1 e to the rt plus c2t e to the rt in case 2. Okay, so that brings us today to case 3. We want to look at what happens when our discriminant is negative. When our discriminant is negative, then what is sitting underneath the radical here is negative, so we're going to get imaginary solutions to our quadratic equation. And we know from algebra theory that we're going to get a complex conjugate pair of roots. We'll call them r1 and r2, and they're going to look like alpha plus or minus beta I, where alpha and beta are numbers that we would know when we go to solve the equation. Okay, so again, the idea is I want to see what solutions can I get? Can I build the general solution? Do I get two linearly independent solutions so that I can build that general solution? Well, we immediately, if we just follow what we've done before, we immediately say, well, if you get alpha plus beta I and you get alpha minus beta I, why don't we just take that first one? R1 we'll say is alpha plus beta I. We were looking for solutions of e to the rt, so we'll plug our r1 into here, and we get e to the alpha plus beta I times t. Using just basic laws of exponents, this is e to the alpha t times e to the I beta t. This is a real exponential, e to the alpha t, no problems here. This is a complex exponential, and there's nothing mathematically wrong with writing our solutions down in terms of complex exponentials. Matter of fact, in some branches of engineering and physics, this is very, very common to do, and there's nothing wrong with it at all. For our approach here, though, we're going to want to write our solutions as real functions rather than complex functions, and so we want to turn this back into a real function. And so you may recall from calculus or algebra the so-called Euler-de-Moivre formula, which says if you have an e to the I theta, that's the same as cosine theta plus I sine theta. So notice our theta here is beta t, and so if we apply the Euler-de-Moivre formula with theta equal to beta t, we get a cosine beta t plus I sine beta t. Now this is still imaginary, So we're not out of the woods yet. But what we've got here is a complex solution to our differential equation. We'd prefer to get a real solution whenever possible, although there's nothing wrong with this. We would like to get a real solution whenever possible. And so to that end, I want to show you this theorem. This theorem says if you're looking at our differential equation and if it has a complex solution, we'll say u of t plus I times v of t, then the real part of the solution, this is the real part and this is the imaginary part, then if you take the real part of the solution and you take the imaginary part of the solution, notice the imaginary part does not include the I, it's just the v of t, then each of those individually will be real solutions to our differential equation. This is very, very important theoretically. If you get a complex solution to our differential equation, then you can extract the real part and the imaginary part, and those will separately be real solutions of our differential equation. You get this sort of 2-for-1 special when you have a complex solution. Let me prove why this is true, and it goes back to things that we did in Chapter 1. So suppose that we have u of t plus I times v of t, and suppose it's a solution of our differential equation. Well, going back to Chapter 1, if this is a solution to our differential equation, it means when I plug it back into our differential equation, I must get a logically true statement. So remember, our differential equation was a y double prime plus b y prime plus c times y equals 0. So if this is going to play the role of my y, I'm just going to put a y here, a y prime here, y double prime here. And if it is a solution, then I must get a 0 because our differential equation was ay double prime plus by prime plus cy equals 0. Now, if I take the second derivative here, I just take the second, treating I just like a constant. I take the second derivative here, I get a u double prime. Take the second derivative here, I get a v double prime. I distribute the a. Here, distribute the prime here, I get a u prime and I get a v prime. I distribute the b. Here, there's nothing to do, I'll just distribute the c. And now if you stare at this, I want to group all of the u terms together and separately from all of the v terms. So the single underlined terms are all the u stuff. The double underlined terms are all the v stuff. If we segregate that, then the single underlined terms give us a u double prime plus b u prime plus c u. We'll put that over here. And then separately, if you look at the double underlined terms, they all have a common factor of I. So why don't we factor out the I? And then we'll have an a v double prime plus a b v prime plus a c v. And if you stare at this, when we have it grouped like this function equals 0. It's a complex function. This is its real part. This is its imaginary part. And if a function is going to equal 0, the only way that that can happen is if its real part is equal to 0 and its imaginary part is equal to 0. That's the only way a complex quantity can be 0. Its real part has to be 0 and its imaginary part has to be 0. So that tells us that this real part must equal 0 and the imaginary part must equal 0. Well, if the real part is equal to 0, then stare at what that is. That's a differential equation in our function u, and it says that u is a solution of our differential equation because when we plugged it into our differential equation, we got a 0 here. We got a true statement. It satisfies our differential equation. Similarly, this says that av double prime plus bv prime plus cv has to be 0. So that's our differential equation, and it says when you plug a v into our differential equation, you get a 0, so you get a true statement. So v must be a solution. So we just proved that u is actually a solution, and v separately is also a solution. They are real functions, and so we've just shown that if you extract the real and the imaginary parts of a complex solution, then those individually will be real solutions to your differential equation. Turns out that we're going to get a lot of mileage out of that, and so let's go back to case 3. If we go back to case 3, we said, well, one solution is going to be e to the r1t. R is alpha plus beta I. I will distribute the t and split this. I'll use Euler-Demar formula to rewrite this in terms of cosine beta t plus I sine beta t. I'll distribute this e to the alpha t to get this plus this. This is the real part of my solution. This is the imaginary part of my solution. So using the theorem that we just stated, if you extract the real part, of your complex solution, then that will be a standalone real solution to your differential equation, while simultaneously, if you extract the imaginary part, that will be a standalone real solution to your differential equation also. So this one complex solution gave rise to two separate real solutions to the differential equation. Now remember our theory. The theory says is for a second order linear homogeneous constant coefficient equation, as soon as you found two solutions, you can build every solution from those two solutions so long as those two solutions are linearly independent. So we're almost home here. We have two solutions. The question is, are they linearly independent? If they are linearly independent, then we'll be able to build our general solution very quickly. So let's check the linear independence. Okay? And I'll leave this for you to do. I believe it's in the homework. The way we check our linear independence is we calculate the Wronskian of this function together with this function. So we want to calculate the Wronskian of e to the alpha t cosine beta t and e to the alpha t sine beta t. I won't show the work here. You can check it on your own. But when you do this, you'll get that the Wronskian is not 0. If the Wronskian is not 0, track with me on the logic here, then we just found two linearly independent real solutions to our second order differential equation. So that says that in case 3, our general solution is C1 e to the alpha t cosine beta t plus C2 e to the alpha t sine beta t. So we found the general solution. Now if you pause and reflect on that a little bit, you might say, well, hold on a second. You never really used that second root of your characteristic equation. You used alpha plus beta I, but you never used alpha minus beta I. How come? It seems like we didn't even use that second root. And you're right, we didn't use that second root. And let's see why it doesn't matter. So what about the root r equals alpha minus beta I? Well, let's just go through the motions again. Let's look at y equals e to my r times t. Let's go through the motions. We know that this is a solution. So again, if we distribute the t and we split the exponential, if we use Euler-de Moivre on this, now if we use just a little bit of basic trig, cosine is an even function, so cosine of minus beta t is the same as the cosine of beta t. Sine is an odd function, so sine of minus beta t, that minus pulls out and you get minus I sine beta t. Now if you distribute your e to the alpha t, you get your real part here and your imaginary part here. Now you do have to keep this sign does go with this quantity. The imaginary part isn't just this, it's this together with this signature, but it does not include the I. So the real part is e to the alpha t cosine beta t. The imaginary part of the solution is negative e to the alpha t sine beta t. And if you stare at these are both bona fide solutions, bona fide real solutions. They are linearly independent from one another, but they're not linearly independent from the pair we already found. As a matter of fact, this is a carbon copy of what we found above, and this is just the negative of what we found above. So it's not that there was anything wrong by, if we included these, it's not that there's anything wrong, but the issue is these don't bring anything new to the table. There's nothing contained in this pair of solutions that wasn't already contained with this pair of solutions. In other words, this is identical to this one, and this is just a scalar multiple of this one. And the theory says, have you found two linearly independent solutions? Yes, then that's all you need. Now you could build your solution set from these two, or you could build them from these two, but either one will do, so we'll just take the first one. Okay, so let's put this into practice. Let's find the general solution of y double prime plus y prime plus y equals 0. So if you want to think of this in terms of a physical application, think of our spring mass system. This would be our mass, this would be our damping, and this would be our spring constant. Okay, so here our A is 1, our B is 1, our C is 1. So our characteristic equation is AR squared plus BR plus C. We'll use the quadratic formula to solve this. It's not going to factor. So after you do the quadratic formula, you get that your roots are minus 1/2 plus or minus I times the square root of 3 over 2. So that means my alpha is negative 1/2, My beta is square root of 3 over 2, and I am definitely in case 3. When I do case 3, then my general solution would be C1 e to the alpha t cosine beta t plus C2 e to the alpha t sine beta t. And I'm done. This is the general solution. In terms of the spring mass system, this is the set of all possible responses of how this mass could move. When you pick different values of C1 and C2, that gives you all the different graphs of the position function that you could possibly get. All right. What if we added initial conditions to the mix? That's one more thing that you'll see in the homework. What if you have initial conditions? So let's just do a different initial value problem, or a different differential equation with initial conditions. So suppose we want to solve the initial value problem, y double prime plus y equals 0, together with the initial conditions, y of 0 is 2, and y prime of 0 is 3. Well, as we've always done with our initial value problems, we have to begin by finding the general solution to the differential equation. This is a second-order linear homogeneous constant coefficient equation. So we're going to find the characteristic equation. Here our a is 1, our b is 0, our c is 1. So my characteristic equation is just r squared plus 1 equals 0. The roots here are r equals plus or minus I. So this one might be so easy that it's difficult. Notice that tells me that the real part is alpha is 0 and my beta is 1. So remember, alpha plus or minus beta I. My alpha is 0, my beta is 1. So my general solution would be C1 e to my alpha t cosine beta t plus C2 e to my alpha t sine beta t. When this simplifies, you just get a sinusoid, C1 cosine t plus C2 sine t. And if all we were doing was solving the differential equation, finding the general solution, we would be done here. But as we've talked about in previous occasions, if you have initial conditions, then all you're going to do is apply your initial conditions in order to nail down the constants, in this case, in your two-parameter family. So I have two conditions. That's going to allow me to find two constants. So I'll begin with the first. Y of 0, I'll just plug in a 0 in for t here. I get a C1 cosine 0 plus a C2 sine 0. And at the end of the day, that has to equal a 2 because that's my initial condition. So I get C1 times 1 plus C2 times 0 has to be 2. That tells me immediately that C1 is 2. To find the other one, so 1 down, 1 to go, I found C1, I need to find C2. I'm just going to calculate the derivative of y with respect to t. So I'm looking at this line, I'm differentiating, then I'm plugging in the 0, and I'm setting it equal to 3 because that's what my initial condition was. When I do that, that gives me, well, C1 goes away, and I get C2 is 3. And so my value for C1 was 2, my value for C2 was 3, and the solution to my initial value problem, remember, don't stop here. This isn't the answer to the question. Remember, when we apply our initial conditions to find the constants, we always want to return back to our general solution and substitute in the value of the constants. So the solution to the initial value problem is 2 cosine t plus 3 sine t. So this concludes case 3. We've now done case 1, case 2, and case 3, so we've completely solved all of the differential equations, ay double prime plus by prime plus cy equals 0. We know how to do that regardless of whether you're in case 1 with 2 distinct real roots, or you're in case 2 with 1 repeated real root, or you're in case 3 with a complex conjugate pair of roots. And we know how to do those when we're just finding the general solution, so we don't have initial conditions, or if we do have initial conditions, and so you're finding particular solutions. You'll find both kinds of those problems in the homework, so give them a try.